is Charese Gates, and today I will be presenting on energy and fusion energy. For this presentation, I use AI-assisted research to gather information from energy.gov, inter.org, and IAEA.org, and my textbook, Physical Science by Bill Tillery. I'll cover what energy is, the law of conservation, different forms of energy, and how fusion works in the sun and in laboratories, the limitations we face, Lehman-Spitzer's role in fusion, and how fusion can impact the world in the future. Here are my resources, AI resources, resources AI got me. EA fusion explanation energy. So what is energy? Energy is the ability to work or to do work or cause change. It's measured in joules. We use energy every day, whether lifting something, powering a phone, or warming food. This image of the word energy helps us visualize how broad the concept is. Everything around us requires energy to function. Now that we know what energy is, let's talk about how it behaves. So, the law of conservation of energy tells us that energy cannot be created or destroyed, only transformed. In this roller coaster example, energy continuously shifts between potential energy at the top of the hill and kinetic energy as it moves downward. So the animation shows that shows a transformation in real time, how the coaster climbs up and is doing a loop-to-loop. It goes high energy, then low energy, and then the loop with fast energy, and then low again. So, types of energy. There are several types of energy. Kinetic energy is the motion that, like moving a car. Potential energy is stored energy, like a book on a shelf. The poster image here helps show what common forms of energy visually. So, chemical energy, thermal, nuclear, radiant, and electrical. Understanding forms of energy is important because fusion converts nuclear energy into heat and light, which later becomes usable electricity. So nuclear energy is stored inside the nucleus of atoms. It is released during fusion, like splitting atoms, or fission, splitting atoms, and fusion, combining atoms. The atom image represents the nucleus where the energy comes from. Nuclear energy is powerful, much stronger than chemical energy, which is why fusion is so promising. Now that we understand energy and nuclear reactions, let's focus specifically on fusion. So, what is fusion? Fusion is the process of combining light, atomic nuclei, and releases energy because the final nucleus has slightly less mass than the starting particles. The missing mass becomes energy through the E equals mc squared. This is why fusion is so powerful. The IEA explains that fusion is millions of times more energy dense than fossil fuels and 4 times more dense than fission. I got that quote from Barbidano 2023. The sun occurs at an extremely high temperature and pressures the core where hydrogen fuses into helium and releases energy as heat and light. That's the same process scientists are trying to recreate on Earth. Fusion inside the sun. Inside the sun, temperatures reach about 15 million C, causing hydrogen atoms to collide with enough force to fuse into helium. The cross-section sun image highlights the core. This is where fusion happens. The energy produced in the core radiates outward and eventually reaches Earth as sunlight and heat. This is the same reaction we aim to replicate for clean energy. Fusion equations. Here's a simple fusion equation. 4H equals He equals plus 4H to He plus energy. H means hydrogen nuclei, which when 4 hydrogens fuse, we get 1 helium nucleus. The small amount of mass lost because energy using E equals mc squared, which is why fusion releases so much power. The equation graph helps visualize the process instead of just reading numbers. Fusion in labs. Scientists try to recreate fusion using devices like Tomascus and stellarators. In this image, the glowing center represents superhot plasma. Strong magnetic fields hold it in place because nothing can physically touch plasma at 100 million C. Major fusion labs include ITER in France, JET in the UK, and NIF in the US. Methods of fusion. There are 2 major approaches to fusion on Earth. Magnetic confinement fusion uses powerful superconducting magnets to hold plasma in ring-shaped tomac or stellars. Interconfinement fusion uses intense laser beams to compress and fuel pellet until it briefly reaches fusion conditions. Research comparing these methods notes that magnetic confinement aims for long duration plasma stability, while laser confinement delivers extremely short, high energy bursts. I got that from O'Hagan Owa 2016. The image here shows both approaches visually, plasma being held magnetically on the left and fuel compressed by lasers on the right. Challenges. Fusion comes with a number of scientific and energy challenges. First, fusion requires extremely high temperatures hotter than the core of the sun to force hydrogen atoms to collide and fuse. Second, controlling plasma at these temperatures is difficult. Containment is a major issue because plasma can't touch the reactor walls. If it does, the reaction stops immediately. Third, producing net power is difficult. We currently face energy output challenges, meaning the reactors often use more energy to start fusion than they generate in return. Fourth, fusion reactions today generally require more energy input than output throughout research process continuing each year. Finally, even if we stabilize plasma, we must protect the reactor structure. Fusion produces high energy neutrons. Radiation damage from 1.41 eV neutrons can weaken reactor walls over time. The image on the side represents the extreme energy environment inside a fusion reactor. Not fire, but super hot ionized plasma. Managing that environment safely inside a fusion reactor is one of the biggest engineering obstacles we solve before fusion becomes commercial. Fusion and fission. Inside the sun, temperatures reach about 15 million degrees Celsius, allowing hydrogen nuclei to collide through the forest to fuse into helium. The fusion process powers the sun and produces light and heat that reaches the earth. According to Tillery 2019, nuclear fusion starts releasing energy as a mass convert into energy. You can see images of how fusion occurs in the core. This is where pressure and temperature are highest, making fusion possible. Fusion development is happening across the world. One of the largest efforts is in the ITER project in France, a collaboration between 35 nations working on to prove that fusion can produce net energy. However, progress has not been without challenges. As reported by Bloomberg 2023, ITER has recently struggled with delays and organization memory loss, causing project leaders to revisit documentation and planning as they push towards operational milestones. This highlights the fusion This highlights that fusion is advancing, but this will take time, investment, and coordination to reach commercial visibility. Meanwhile, other countries are making breakthroughs. In the United States, the National Ignition faculty has achieved ignition conditions using laser-based fusion. In China and South Korea, reactors like East and K-Star have reportedly recorded plasma confinement durations. These developments show that fusion is a global priority, with multiple research paths underway. I got that from Bloomberg 2023. Okay, future benefits. Fusion energy offers several promising future benefits. It produces clean energy with no greenhouse gas emission, unlike fossil fuels, which makes a strong option for climate change efforts. It also generates less long-lived radioactive waste than fission, improving long-term safety. Fusion fuel is widely available. Deuterium-formed water and deuterium bred from lithium provided abundant supply. Webster 2023 explains that fusion could be a safe global scale energy resource that reduces fossil fuel dependency and supports stable electricity generations without greenhouse emissions. A more recent perspective from MIT Energy Initiative suggests that successful commercial fusion could significantly reduce global decarbonization costs as an act. A continuous base power source. Malpanja 2024. The image represents future power systems that could run fusion instead of fossil fuels, potentially powering cities, industries, and even spacecrafts in the future. First, outlook and grid integration. Now that we've talked about the benefits of fusion, let's look at what it could mean for our energy grid in the future. Fusion has a potential to supply large-scale electricity to cities, acting as a clean base load power source, meaning it could run continuously, unlike solar or wind, which depends on the weather. If fusion can be scaled successfully, it could replace fossil fuel power plants and help dramatically reduce carbon emissions worldwide. Fusion fuel has a deuterium is abundant in seawater, so long-term fuel supply is not a limitation. According to the National Academies of Science, fusion could eventually be connected to the U.S. power grid, but it will require advanced plasma control reactors, materials, and government and private funding. The image on the side represents a Tomahawk-style fusion concept with a glowing plasma core, symbolizing future fusion reactors. The blue ring represents magnetic confinement that holds plasma in place, and Bring's center represents the energy that could someday power homes, businesses, and even spacecrafts. This shows that fusion is not just theoretical, it is a real possibility for the future of clean energy, and scientists believe it can be achieved with steady progress and investments. My summary. Today we learned that energy is how it transforms, and how nuclear fusion works in stars and labs. We discussed why fusion is difficult but promising, and how it could benefit our world long term. The summary image serves as a visual reminder of major ideas. These are my sources that I use throughout this project. I use AI tools to help me collect information and summarize my research. Thank you for listening. And here are my more resources that I used.